Hello, everybody. Welcome to our second class. Recording is in progress. We received a question from your colleague. Some student they didn't read the announcement. So to access the class recordings, you will go to the following link. It's available in our course description. So if you go to OWL, open our course tab. In the overview, you will find at the end the YouTube playlist link. Once you click it, you will find all the videos. They will be numbered in sequence 1, 2, 3, 4, 5, depending on our class progress. So I hope this is clear. Also, after the class, I will send an announcement that contains a link for a Google Sheet. In the Google Sheet, you will add as groups, you will add your names in the group, and there are two sheets in that Google Sheet. The first sheet for groups, the second one for those individual. Some student, they might come and said, hey, I don't know anybody, so I don't know to which group I'll be in assignment 3. So sorry, put your name as individual. Put your name as individual on that sheet, and we will manage if there is a group like has less number, 2 or 3 students in the group, we'll add you to that, or we'll form from those individual some groups. As our class is huge, almost 162 students till today, I will make the minimum as 5 and the maximum as 8. Minimum as 5, maximum as 8 students. So is that clear? Because I received a question chat regarding the group size. Yeah, I'm not sure the reading week when it will be. It will be the week after reading week on a Friday, because as I mentioned in the course outline, that the midterm will be conducted in the tutorial session. But I'll not make it 8:30, I'll make it from 9 to 10. I'll make it from 9 to 10. Is that clear, guys? Any other questions? You are welcome, Dima. I'll start with handout 1. And if you see before the class, normally before the class, I will upload the class note. Those are equal if I wrote something on the board. So we'll go through the handout, then through the class notes. Let me open handout 1. I'll share my screen. Everybody can see my screen now? Yes, no? Yes, sounds good. Okay, so we'll start with our first handout. As I informed you guys that this course it's a dry material, but we'll try our best to make it as much as we can fruitful. So in the first week, we'll have an introduction and deterministic finite automata. So it's an introductory handout, and we will discuss the deterministic finite automata. What do we mean by those? We will see. So this slide, because these are the handout of Professor Essex, who used to teach this course, and maybe next year he will back to teach this course. So normally I tried my best not to make a lot of changes in the course. So this website is not working, and the lecture schedule and So this is for the textbook, which is a Spicer and the other recommended textbook. So this slide, these websites, I'm not sure if they are still working. However, it's for an old version that taught last time by Professor Essex. What this course about? What this course about? Why learn about theory of computation? So, you as a software engineer, it would be very useful for you to get some basic concept and understand the basics of computation. What do we mean by computation? What computation can do, what cannot do. All of these information are essential for a software engineer. So in this course, we will explore some of the fundamentals question in our field. What is computation? What do you need to perform a computation? What problem can you solve with a computation? What cannot? You will ask me, is there some problem that we cannot solve it? Yes. Till today, there is no solution for those problems. Of the problem with solution, which are easy, which are hard? Do we have hard problem? Yes. Do we have easy or soft problem? Yes. All of those information will go through the term. So, like some historical information, that in 1822, the Charles Babbage was dreaming to have a machine to perform calculations. Inspired by the idea of his colleague, Ada outlines the first software program. So Charles Babbage is considered like a father of computation or a father of computers, because he's the first person who worked closely and found some machine that can do calculations. 1900 to 1928, Hilbert proposed a set of 23, the greatest of as of then, and solved the problem in mathematics. So the second and 10th of Hilbert problems eventually lead him to propose like what we call it nowadays, decision problem. So the question is an algorithmic means of deciding whether a proof exists for a given logical statement or not? Then in 1936, Turing and Church prove no to the decision problem and introduce what we call it a universal model of computation to do. And we start calling it Turing machine. And it will be in the final exam material. I don't think we will reach it in the midterm material. Guys, can anybody told me what is the first computer that a human saw? No, not Turing. Yes, Ryan. It is the abacus. Do you know what is abacus? When you are a kid in grade 1 or 2 and they will start to teach you math, you start moving not the calculator, the abacus. So the abacus were used to do some simple math, to add a small amount of numbers. So this is the first computation machine that the human find. No, in computation, there's a difference. Abacus is used for calculation, yes. However, the calculator that's founded by Charles Babbage is different than abacus, which is a form of simple calculator that can add, subtract, multiply, and divide numbers. But the abacus can use for addition and subtraction only. So not all of these topics we'll talk about it in our course. Most of them will take under consideration, even we'll touch base with them. So Chomsky described hierarchy of formal grammars with important application of programming languages. So he has a lot of valued work toward the programming languages. 1971, University of Toronto Professor Koch proposed P versus NP. What do we mean by those? We'll discuss them in handout 8 and 9, I believe. So this Professor Koch, introduced one of the open problem till today in computer science that couldn't be solved yet. 1994, Peter Shor proposed to run the quantum computer that would efficiently solve the integer factorization problem, which would break the RSA and related public key cryptos to secure digital communication. So this was founded in 1994. So what are the notation that we will deal with during this course? The first one, the set Z with 2 lines between the upper and lower dashes in Z. What is Z? It's the integer set. So to start from minus infinity to positive infinity for integers, which mean -2, -1, 0, 1, 2, 3, 4, etc. What do we mean by the natural number? Natural number is a subset from Z, and it will take the positive integer without 0. It's 1, 2, and till infinity. Set builder. What do we mean by set builder notation? The set builder notation start with this brackets, then we will name it, then we will call or explain what is the condition. Translation, the set of all x's, which statement is true. Some use dot instead of the column, or some use colon instead of this line. What is x belong to z, which mean this is the condition, x is greater than 0. Is it true or false? Answer me, is this true or false? Guys, do you hear me? Hello? Okay, Alex, can you just unmute your mic and tell me why it's false?
Could you repeat the question? I think I might have misinterpreted.
Okay, the statement saying the set of x's that belong to z where x is greater than 0. Is this possible to have value? For example, if we said 3.
Yeah, if you said 3, yes, but
if I said 1,
it's not. Well, yes, but if you had a negative integer, Yeah, it wouldn't be possible because it's not bigger than 0.
So when we say X belong to Z, it shouldn't be whole Z.
Right, it should be the subset that meets the condition.
Yep. So is that clear, guys?
So the answer is true.
What do you think?
I think it's true.
Translation: the set of all X's for which statement is true. So which mean that X's is N here. N will make an answer for all X's, and we said that N is a subset of Z.
Oh,
Which
so
mean, yeah,
just
which
a
mean
set
it
of
is,
notation statement for integers to natural numbers. So it's
yeah,
basically proving natural numbers above 1, and that's how, like, the condition that you define it.
so when we will not take the whole Z, we'll take the 1 and above. Clear? You will have more info, and I will remind you with the set theory. We'll have a full explanation of set theory. Don't worry, guys. So a set is an unordered collection of elements. So the set is an ordered collection of elements. For example, let A equal a set of x1, x2, x3, and x4, and B is a set of x4, x5, and x6. So element order, does x1, x2, x3, x4 equal x4, x3, x2, x1? Yes or no? Yes, because we said it's unordered. So two sets are equal if each member of the first set is available in the second set, whatever the order. Set membership. Which statement is true? X1 belong to B, X1 don't belong to B. Is X1 available in B? True. So the second answer, so this is the correct answer. Subset, which is a state, which statements are true. So to make a subset, we use this number, this symbol. So X1 is a subset of A. X1, it's the same. X1 is a subset or equal A. X1, X2, X3, X4 is a subset of A. X1, X2, X3, X4 is a subset or equal to A. So which are true and which are false? So some will say all true. Some are saying last three. All but last one. One, two, 4, and 5. Three and 4. Okay. So the first two are the same, right? So X1 is a subset of A. Yes. x1 is a subset or equal to A. Also true. But what is the mistake here? The first three are wrong. Why? Who can tell me? Not a set. Yes. Andrew, thank you. Should be between the set brackets. Yes. That's correct. So the first three are false. We should, in order to say a subset, so it should be in a set format. Set format start with this bracket and end with this bracket. So the first three, they are false. The second two, they are correct. x1, x2, x3, x4 is a subset of A or a subset or equal A. So the last two are correct because they are in a set format. Clear? A set is an unordered collection of a unique of elements. Let A, x1, x2, x3, x4 power set. Set of all subsets. So what is the power set of A? It is x1 alone as a set, x2 and x3 and x4. And it's x1, x2 or x2, x1, x3 or x1, x4 and any possible subset of A, we will call it a power set. So this symbol, some of you, if you go back to math, you will say this is the absolute value. No, that's absolute value. Here we said it's the length of the set. So it is 2 to the power length of A. What is the length of A here? What is the length of A here? 4. So it is 2 to the power 4. So the power set consists of 16 subsets. Okay. Set operations. What are the operations that we might have on the set? The first one is union, which means X where all X belong to A or X belong to B. If we find a shared one, we'll not repeat them, we'll make it one. Like X4, it will not be repeated X4 and X4. So what is A union B? Intersection, which is X where X belongs to A and belongs to B. Here we have only X4. Here we have only X4. Cardinality, which is the length, which is the number of elements in A, or we call it a length in programming. How many elements in that set? We call it cardinality of A. So if we back here, what is the cardinality of power set? It is 2 to the power of cardinality of A. Is the cardinality of B? What is the cardinality of A here? Guys, cardinality of A, 4. Okay, is the cardinality of B greater than the cardinality of A? Yes or no? No. Let A equal the subset 1, 2. What is the cardinality of A? 1, yes. We'll consider this as one element. If we ask about the cardinality of this subset, it will be 2. But the cardinality of A is 1 here. A is a set that contains one element, which is the set of 1, 2. Let C equal phi, which means the empty cell or the empty set. What is the cardinality of C? Okay, some saying 0, some saying 1. The cardinality of phi is 1 or C. Okay. First observe equals 0. The empty set is a set containing no elements. On the other hand, C to the phi equal 1 because C is a set containing one element, and this element is the empty set. Is that clear? So the cardinality of C is 1, which is the empty set. It has one element, which is the empty set. Is that clear, guys? Tuples. What is the difference between set and tuple? Tuple is an order list, and we use the left and right parentheses. So TIJ, no, it's the same like C equal 5. So this is not 0, no, it's 1 for your question. So a tuple is an order list. Here the order is important. So A equal x1, x2, x3, and x4, and B x4, x5, x6. Element order, does x1, x2, x3, x4 equal? No, they are not equal because it's a tuples. Cartesian product of A times B, or Cartesian product, which is A belong to A and B belong to B. What is A? The Cartesian product between A and B as a tuples. Cartesian product of multiple set A times B times Z. For A, B to Z, A belong to A, B to belong to B, Z belong to Z. So here, for example, x1, x4, x1, x3, x1, x2, x1, x1, etc. So this is the Cartesian product. So you have this question. To be solved by you guys, and next class tomorrow I need some volunteer to answer it and explain it to the class. Each class will have similar questions, and those questions you will have a bonus marks that if you lose like marks in midterm or final, that will recover what you lost. 1, 2, 3 marks based on your participation in the class during the term. So this question to be answered next class in slide 13. Functions. As you remember in math, that the function is denoted normally by F colon A to B, which is a mapping between a set of input in A and a set of output in B. What do we mean by functions domain? It's the set of possible input. What is the acceptable input for this function? We call it the domain. What is the range? It's the set of output. So each function has a domain and range. The domain, which is the set of input, and the range, which is the set of output. The codomain is a set B in which all output fall. The image is the subset B prime, which belongs to B of the codomain into which all the elements of the domain are mapped. We will clarify this with examples next class to make things are clear. And we'll use this function with the domain and image and range in handout 6 and 7. Example, let f z, the input falls within the integers and the output is an integer. Fx equal x square will lead to x square. For in mathematics or in calculus, you'll have it f of x equal x square. The domain is z. The image is n node, which is 0 plus the natural number, which is 1, 2, 3, the integers. Why the image is positive, including 0? Who can tell me? Because if you square any two negative numbers like -2 square, it would be a positive number. That's why. Except the 0. So it's 0 union the natural number set. Is that clear? Multiple variable example. If we have a function that has an input z and z, then the output would be in z, where f of xy lead to x square and y square. So f of xy equal x square and y square. So we'll take two input from z, and the output would be also from z. What do you mean by alphabets and the string? Alphabet, we give it the simple sigma, is a set of symbols. Sigma equals 0, 1 is the binary alphabet. If you go to the binary language, it consists of two, the alphabet of that language consists of two symbols, 0 and 1. So, hey, what is the alphabet, which is A, B, C, D, X, Y, Z? Who can tell me? Who can answer this question? English alphabet, it is the uppercase or the capital letters of English alphabet. Clear? Thank you, Tony, Ryan, and who else? Nicholas, for answering. But it's the uppercase of English alphabet, or what we call it, capital letters. A string is a finite sequence, which means when we are saying finite, guys, that means it has a known amount of states, of symbols, of numbers. It's not infinite. Of a given alphabet. Let A, B, C, D, Z. Is password a valid string? Yes. Is password 1 a valid string? No, because 1 is not an element of that alphabet. Clear? Let sigma equal 0 and 1, which is the binary alphabet. Is 0 a valid string? Yes. Is 0, 0, 0, 0 a valid string? Yes. Is 0, 0, 0 infinity times a valid string? Yes or no? Yes, it's no. Because we said the string is a finite sequence of symbols. And the third one is not finite. Those are finite, yes. The third one is not finite, so it's no. So keep in mind that a string is a finite sequence of symbols. This simple epsilon denotes the empty string. It functions as identity element. Think of adding a 0 or multiplying by 1. So what is the cardinality of epsilon? What is the cardinality of epsilon? 1, yes, great. What is epsilon 0, epsilon 1? And what is epsilon 0, epsilon, epsilon 1? Next class, a volunteer will answer this question and explain why. Now we have slide 13, a question in slide 13, and the question in slide 16. Okay, guys? Now, we'll talk about powers of an alphabet. Sigma to the power k is the set of strings of length k. So let sigma equal 0 and 1. Sigma to the power 0 is the epsilon. Sigma to the power 1 is 0, 1. Sigma to the power 2, what it's equal. Another volunteer will answer this next class. So 3 volunteers will be needed tomorrow in tomorrow's class to answer a question in slide 13, 16, and 17. And another, the 4th volunteer will answer what do we mean by clean star, sigma star. The answer is here, which is sigma 0, union 1, union 2, etc. So, what do we mean by clean star? With example, the 4th volunteer. So, clean star is infinite. All elements of clean star have a finite length. So, the volunteer will clarify what do we mean by clean star. What do we mean by concatenation? Which is merging two strings together. Concatenate. And if you have Java or Python or C++, you'll know the concatenation and you took it in the programming languages courses. So let's sigma 0 and 1, and A is 0, 0, B is 1, 1. Then concatenation of A and B is 0, 0, 1, 1. AB squared. What is the answer? A square, B square. So AB squared will be AB, which is 0, 0, 1, 1, 0, 0, 1, 1. This one, A square, B squared will be AABB, which is 0, 0, 0, 0, 4 ones. Formal language. What do we mean by a formal language? Guys, this class is very rigid, I know. It's all definitions and symbols. And some set theory refresh. But all of these things will be repeated during the term with different topics, so don't worry. A formal language over alphabet sigma, denoted by L, denote a language, is a subset from sigma star of that language. It is basically a set of a string the kind of formal languages we're interested in are ones that can be produced by some kind of rule. So once we have a rule on those in this language and sigma star, then we'll have the language and strings of that language. So let sigma equal 0 and 1. What language is 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. So what is this language? It is the language of string that end in 0. Okay, just give me a sec to switch off the clock. Okay. What is the language 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0? It is the language of a string that have at least one. That it has at least one occurrence of the digit 1. Okay? How does this differ from natural language like English? How is it similar? Now we'll answer the question, what is computation? So programming or computation, it's like if you ask a question and you get an answer. For example, if you have the equation y equal x squared, and I say that let x equal 3, find y, then you will answer 9. That's how computation occur in effects. But for this course, and indeed for the purpose of studying computation, we are going to pose a question from computation as decision a problem. So we will asking yes or no. Is the point 3 and 9 on the curve, yes or no? This is the way that our course is gonna work. Is this representation give deterministic finite automata to the following problem, yes or no? Correct or wrong? This is how we will go. Informally, computation is modeled as answer to yes or no question. More formally, what do you mean by computation? Given the description of some language L, giving an input string S, compute a yes or no answer to the following question. Is S belong to that language? Yes or no? That is, does L accept S, or L does not accept S? Then we will use the term reject S. So the computation is in the form like we will decide if S belongs to L or not. The string belongs to that language or not. I'll give you an example to understand what I'm saying about. For example, if you write a code in Java, is that line of code is correct, belong to Java or not? Accepted by Java or not? If you have a syntax error in the command, does the Java compiler will accept that statement or not? No, it will give you an error, right? So computation, we will study the string if it's accepted by that language or not. Is that clear? Okay, would you like to have a break or shall we continue? Yes, Nicholas, at the end, yes or no? Yes or no, it is 0 or 1, which is the machine language that the computer understands. So guys, shall we have a 5 minutes break or continue? Continue, okay, let's continue to finish earlier. Okay, now we'll start with what we call deterministic finite automata, DFA. What do we mean by deterministic finite automata? So, the formal definition. A deterministic finite automata is a 5-tuple Q, sigma, rho, Q naught, and F, where Q is a finite set of states, sigma a finite alphabet. Some call this is delta, which is a Q, the Cartesian product of a Q with the language or the alphabet, and it will give us the output in a Q, and we call it a transition function. Q naught, which is the starting state. From here, we start computation. F, which is the final state or accepting state, or the final state. We stop here. So Q naught, we start there. F, a set of accepting state. Sometimes we have one accepting state or more. Depend on this question and the statement and the constraints put to that example. Question till here. Okay. So Q naught, Q1, they are the states of a DFA, which is the set of state Q. A finite set of states. We have a known number of states. Here we have 2 states. So Q is a Q0 and the Q1. Alphabet, which is 0 and 1. Transition function. If I'm in a Q naught and receive a 0, I will stay in a Q naught. If I'm in a Q naught and receive a 1, I will move to Q1. If I'm in a Q0 and receive a 0, I'll go to Q1. And if I'm in a Q naught, this is a Q1, I believe. This is Q1. This is a mistake, typo mistake. If I'm in a Q1 and I receive a 0, I will stay in a Q1. If I'm in a Q1 and receive 1, I'll go to Q naught. So here, I'm in a Q naught. If I receive a 0, I'll stay in a Q naught. If I receive a 1, I'll move to Q1. In a Q1, if I receive a 0, I'll stay there. If I receive a 1, I'll go back to Q naught. Okay. Initial state, we start at a Q naught. And accepting state F is a Q1. So here we shall stop. Here we shall stop. And normally we make it double circle. You see here to indicate this is a final state. And with the word start or without it, this arrow show where we start. Clear? With the start or without it, the word start or without it, but this arrow show us that we started at a Q naught. Sometimes they make it like diagonal, whatever. Once I see this one and nothing before it, that means we start here. Clear, guys? So this is a language, and we have this DFA, deterministic finite automata. Can anybody answer me what does this language accept? Of course, binary. The alphabet is binary. But what is the condition? There is a condition here. This is the alphabet. We mentioned this, guys, that this alphabet consists of 0 and 1. But with this language, what does it accept? Think about it. It would accept any binary numbers. It would accept any binary numbers that either end in 0 or 1, right? Here they call it a Mealy machine. Is a finite state transducer that it's either accept 0 0 or 1 0 1 0 0 1 to be end here. So this is what we call it, finite state transducer, FST. But we'll not go and discuss it in deep details, this one. If you wanted to know more, anything in the pink color in our handout, if you press on it, it will open the wiki page about this topic if you want to read more about it. I didn't mention that at the beginning. For now, we will focus only in yes, no problem, hard enough as it is. That is an automaton. When we say automata is a plural, and the singular of the word automata is automaton. Either accept a given string or does not accept it. The notion of output will become clearer when we talk about Turing machines. Turing machines have a tape that can leave behind a result. So I will discuss this when we have the Turing machine. I think in chapter 5 or week 5, I'm not sure. Where is the remaining? Okay, So we had done with the first handout. We'll go to the class notes just to explain some. They are repeat something, but can you see my screen now? Okay, sounds good. Now, what do we mean by a computation? Step-by-step solution to a problem. For example, if we have a multiplication of two numbers, finding a word in a dictionary, checking whether there is a path between two vertices in a graph. So this is a computation. What do we have? Computational devices, calculator, your cell phone nowadays, computer, pen and paper is a computational device if you do some calculations. In this course, we will study computational devices based on the resources that use. First computational device in this course is a finite automata, which is a computational model which has a certain finite amount of memory. Why we mention at the end of the class that those things could be discussed further or studied further when we use Turing machine, because your Turing machine has an advanced memory model, which is the tape, which is better than the previous 0 or 1 computational model. So the finite, deterministic finite automata, we don't use a memory. We don't have a memory with this model. So that's why it's more complicated and we cannot solve a very huge and big problems. More specifically, finite automata has a state, and the number of states in a model has a finite number of states. Automata is the plural of the word automaton. For example, in the finite automata, if we need to present an electric switch, which is either on or off, with the simplest electrical switch that we have, which is on or off. So if you push it, it will move to on. So we have two states, off and on. And the action or the transition will happen with the push. If you push the button of the electrical switch, it will go to on. If you push it again, it will back to off. So that the transition between states will be pushing the button. Push is the operation. Another example, if we have a fan regulator, which has 4 modes. 0, which is off mode, 1 is low, 2 is medium, 3 is high. So the operation will be clockwise or anti-clockwise, right? So if we are at off and we go clockwise, it will go to 1. If we go with the clockwise again, it will go to 2. If we go to clockwise again, it will go to 3, then it will go to off. And if we go anti-clockwise from 0, it will go to 3. If we go from 1 to anti-clockwise, it will be off, and so on. So this represents the fan regulator that has to move in both directions, clockwise and anti-clockwise. And at each state we are, if we go clockwise, where we will move, and if we go anti-clockwise, where it will send us to the new state. Is that clear, guys? If we have the following operation, C clockwise, clockwise, A clockwise, clockwise, A, we will end up at stage 2. Let's see. We are at 0, here the start, clockwise, clockwise, anti-clockwise, then clockwise, clockwise, anti-clockwise. So we will end at this stage. Math example, if we have a math example, if we have a binary number string L equal X, where X is a binary string divisible by 4 or divisible by 4. So what are the numbers that divisible by 4? Like 4, it is yes. 6 no, 12 yes. So we observe that the set of binary numbers that divisible by 4 are exactly those that have 0, 0 as a suffix. So the question is, can we design a finite automata that accept all string in this language which end by 0, 0? Let's see. If we start, here we have 0, 0. Then we have 1, it will be 0, 1. And if we have 0, it will be 1, 0, and all of those. So start state is 0, 0, accept state is 0, 0, this one. If we have a string 1, 1, 0, so 0, 0 with 1, we will go to 0, 1. Then if we have 1, we'll go to 1, 1, and we have 0, we'll go to 1, 0. So this is not accept state by the language. But if we have this one, we'll go to 0, 0. When 1, we'll go to 0, 1. And then another one will go to 1, 1. Then we'll have another 0. It will be end by 1, 0. Then another 0. It will end by 0, 0. Then the string is accepted by the language. Here, I'm taking like a partial graph from here. So here, if we have 0, 0, whatever we have zeros, we will stay at the start state, and which is the accept state itself. So we have the start and end state is the same. If we have 1, we'll be here at 0, 1. Then if we have a 0, it will be 1, 0. Then we'll have a 0, it will be 0, 0, and so on. So we studied all the cases here. We studied all the cases. So this is a reject state or not accept state in this one. And here we have an accept state of this one. So this is what we have for today. Tomorrow we'll answer the question by the volunteers, then we'll move to handout 2. Any questions? If you don't have a question, you are free to leave. If you have a question, you can stay and ask your question. And see you tomorrow, guys. Thank you, Robert. Thank you, Noah. Thank you, everybody. Thank you.
Thank you, sir.
Timmy, you can wait, so we'll answer your question. You can unmute your mic and ask your question, Timmy.
I was just wondering, in the examples at the end, when you're going from like state 0, 0 to 0, 1, like, are you just adding a 1, or like, how are you transitioning between states?
Okay, so let me share my screen again. You mean in the last one, right? In the class notes, right?
Yeah.
Okay. Here?
The last 2 examples.
Yeah, here we said if we are given this string, is this string going to be accepted by the language or not? So here, based on the language that given by the question, so it's 1, 1, 0. So we start at 0, 0. If we receive a 1, then it will be 0, 1, right? Then we will receive the second one. And here, if we receive another 1, we'll go to 1, 1. Then we will receive a 0. Then we will be in at this state. Is this a final state?
No.
Based on the language description, no. Here's the final state, right? So this one will not be accepted by the language. And another example, we said, assume that you have a string that consists of 1, 1, 0, 0. Is this going to be accepted or not? Let's back to the original. We have 1, 1, 0, 0. So here's the 1, will be at 0, 1. Then we receive another 1, will be at 1, 1. Then here we receive a 0. Then the last 2 digits is 1 0. Then we receive another 0. Then we'll end at 0 0. So it will be accepted because we end at final state. Is that clear?
Oh, yes, thank you.
You are welcome.
Sorry, is that how we check if it's acceptable language? We just look at if it ends up at the final state?
Yeah, you will see now we'll have 2 types of questions of this deterministic finite automata. Either you have a language drawn and we ask you about cases, or we give you the rules, the alphabet, the string, the transition function, and you will draw the DFA.
Oh, okay.
But we'll have more example during the coming classes, guys. Don't worry. We'll have enough amount of examples.
Right.
You are welcome.
Thanks.
Any other questions, guys? If you don't have a question, you are free to leave.
Hi, sorry, I had a question.
Yeah,
I
Amanda,
was-
go ahead.
Yeah, I was unable to attend the first part of class today. Will the lecture be posted soon?
Yeah, so normally, like, we have the 2 classes, one after each other.
Mhm.
So tomorrow we'll have classes. Normally on Friday, I'll do the format and the HD version of the video, then I'll upload it to YouTube. So maximum by Friday, you will receive it.
Okay, thank you.
You are welcome. Nipona, Perez, do you have a question? Manasha? Kenneth? I'll stop recording here. See you tomorrow. And have a nice day.